Hello and good afternoon, everybody. My name is Kamran Khajipur. I work as microscopy and microanalysis product manager with AXT. I'm pleased to open the introduction to this webinar conducted by AXT in collaboration with one of our much valued customers, Dr. William Ricard from Curtin University today. Just a brief introduction about AXT. AXT is a dynamic distributor for high-tech scientific instrumentation in Australia and New Zealand. We have a large product range covering microscopy, microanalysis, nanofabrication, and tools related to nanotechnology. We take pride in building a strong partnership with our customers and suppliers, bringing together the best in scientific innovation and research with the cutting-edge scientific instrumentation, truly unique solutions that we supply for the research industry in Australia and New Zealand. So today's presentation will be done by Dr. William Ricard. I'll introduce him very briefly in a few words. Will works as a senior research fellow at the John DeLaider Center at Curtin University in Perth. He is the facility leader for FIB-SEM in the center and has a decade of experience with all the techniques actually associated with FIB-SEMs. So he's been using ToF-SIMS on his FIB for a few years, and he's got maybe one of the most extensive experiences with this technique, at least in Australia, and I'm sure even around the world. So his research interest, as you see, includes nanoscale characterization of geological materials using advanced analytical techniques, and I'm sure he will be talking about those in more details in his presentation. We'll leave it with William Ricard to start his presentation. So over to you, William.
Hello, everyone. Thanks for joining today. So as Cameron mentioned, I've sort of worked in recent years a fair bit with this technique, and it's a emerging technique. So there's not a lot of experience out there, and so I'll just sort of go through and mention a little bit about some of the work we've done, and specifically in the applications. So I'll just share my presentation. Okay, so I'm based at Curtin University in Western Australia, and the analytical facility we have there is the John DeLaider Centre. And so we have a range of electron microscopes and mass spectrometry instrumentation. The really neat thing about this particular technique is it actually links mass spectrometry with electron microscopy, and there's a number of advantages, and I'll kind of go through them in this presentation, as well as some theory and some background information. Okay, so so discuss a little bit about exactly what, for those people unfamiliar with FIB-SEM in general, I'll briefly introduce that, and then ToF-SIMS as a standalone technique, and then the combination of the two. And finally, I'll kind of finish with some specific applications of the research we're doing here at Curtin University. So focused ion beam scanning electron microscopy is a very mature technique nowadays. I think you'll find most major universities have one of these instruments. They're extremely versatile. They're used for a range of applications, and it's really the combination of the electron microscope for imaging and the ion column for milling, depositing, and some more material science applications, ion doping, deposition, and so forth. And so conventionally, most people are using these microscopes for site-specific sample preparation, and I think you'll find a lot of FIB-SEMs around the world are almost purely doing TM specimen preparation, and probably to a lesser extent atom probe specimen preparation. And they're fantastic for that. Gallium fibs are very high resolution, and you can extract pieces of material from a very specific part. However, FIB-SEMs obviously can do a number of other things, and so 3D slice and view is a very common technique used in FIB-SEM. Cross-sectional analysis, people use it for nanofabrication, and more recently, people are looking at analytical applications in FIB-SEM, and one of them is ToF-SIMS, and that's what I'll discuss today. So time of flight secondary ion mass spectrometry. So it's a SIMS technique, so where we're looking at the secondary ions which are sputtered from the surface, so the primary ion comes in and sputters a number of atoms away. Most of them are actually neutral, but some of them are actually charged as secondary ions. And then if we extract those secondary ions and pulse them through a time of flight analyzer, we can actually identify these ions by their mass to charge ratio. And this is a fairly mature technique as well as a standalone instrument, and there's a number of manufacturers making ToF-SIMS instruments, and they're largely used in the organic analysis and surface analysis. However, more recently, and it's probably only been 3 or 4 years that manufacturers have started to put ToF-SIMS instrumentation onto a FIB-SEM. So you've already got your primary ion source, and this is just a mechanism to collect the secondary ions that are being generated every time someone's doing sputtering with a FIB-SEM. And so the way that occurs is the gallium, in this case on a TESCAN LYRA 3, the gallium primary ion beam sputter the material away. There's a ion transfer optics to extract those ions, and then it's pulsed through a time of flight reflectron, and then the ions hit the detector relative to their mass to charge. And one of the real advantages of having that on a FIB-SEM is because of the probe size. So the FIB-SEMs operate with a liquid metal ion source, particularly gallium FIB-SEMs. So there are plasma FIB-SEMs which use a different source, but the liquid metal ion source is able to achieve very, very small probe size, which has a number of advantages for ToF-SIMS. So as I just mentioned, so the gallium liquid metal ion source can generally achieve smaller probe sources sizes than some conventional SIMS ion sources such as cesium and oxygen. And so that allows us to produce elemental maps with very high spatial resolution. And I'll show you a little bit why, because the interaction volume or the information volume associated is very similar to the size of the probe size, whereas in comparison to electrons where it's not. And the SIMS also has a number of other advantages, including surface sensitivity, light element analysis, and isotopic analysis. And from that, we can generate the SIMS maps, as you can see here on the left, or we can look at mass spectra. So the ToF-SIMS we have on our FIB-SEM, so we have a TESCAN LYRA FIB-SEM, and we have a ToFWorks ToF-SIMS compact ToF instrumentation, and the published kind of specifications for this particular detector is lateral resolution better than 50 nanometers, so you can see that's already significantly better than you'd likely achieve with something like EDS and SEM, which would be closer to half a micron or greater. Depth resolution, and this is a really nice one. So for depth profiling or thing, we can get better than 20 nanometers, and I'll show you some applications of that later on. Detection limit. So it is listed here as sort of in the ppms, but I've sort of added a little caveat that's very element dependent. So I'll show you a little bit why. Effectively, you have to ionize that element efficiently to be able to detect it, and some elements will ionize easier than others. Mass resolution, So the mass resolution is sort of moderate. It's enough to differentiate between different elements in general. However, there are some interferences which are problematic. Dynamic range, and this is quite a neat thing. You can measure trace elements and major elements at the same time, and that's very useful. The final specification there, required vacuum. So this can be a bit of a challenge in a FIB-SEM where you often venting the chamber and loading samples. So you can achieve a good vacuum, but you won't achieve an ultra high vacuum. So one of the kind of considerations with this technique compared to say a dedicated ToF-SIMS is you will have not as good vacuum as you'd ideally like for SIMS, and there you just have to take into account some contamination effects, which can be mitigated by sort of pre-sputtering and so forth. And so where we see this in this kind of common schematic about different analytical techniques, we see kind of ToF-SIMS as a sort of technique that kind of links some of the coarser analysis, such as laser ablation, with some of the very finer analysis, atom probe, TM, and STEM, and so forth. So it's really nice that if you're preparing a sample for TM, that you can do your surface analysis maybe by EDS, but maybe that's a little bit too coarse. So if you do ToF-SIMS, and then that's got to helps to correlate that information right down to the nanometer length scale, which you'll be using with TM or atom probe. Okay, so just as a little bit of theory, which helps you understand the detection efficiencies, is so the primary ion beam is sputtering a lot of material. You know, in gallium FIB-SEM, you can be removing microns of material. However, only around 1% of that sputter material actually is charged. Most of it is neutral, and if for the neutral atoms, we can't extract them and detect them. So effectively, 99% of the signal is lost. And the amount that is actually ionized depends on the the electronic structure of the material. So the first ionization potential. And another point there is that they can either be ionized positively or negatively. And so that means some, if we're using a bias to attract the ions over, we need to change that bias depending on whether we're trying to target positive ions or negative ions. And one of the nice aspects of this particular techniques is we can change between positive ion analysis and negative ion analysis in just a couple of minutes with very little alignments. Okay, so what the way in SIMS that people generally compare the sensitivity for a particular element is to compare it to a baseline element, and usually that's silicon. And so from that they generate what's called relative sensitivity factors, and so the sensitivity of a certain element in comparison to silicon. Now there's a lot of data published for cesium and oxygen because they're common SIMS sources, but there's much less published for gallium. So there's a paper by Stefan where he publishes some gallium RSFs, and I've sort of generated that into periodic table for positive ions and negative ions, and you can see that there's some information there, but there's also missing a lot of elements. So generally speaking, for ToF-SIMS, until there's some better published values for gallium, I generally use the published values for cesium and oxygen as a rough guide, and it tends to work quite well. And so what you see here is the orange coloured boxes being the high sensitivity, and the grey basically no sensitivity, and sort of then this is for positive secondary ions, and this is for negative secondary ions. So in positive secondary ions, our alkalis, our rare earths, and more or less most of the left side of the periodic table, we have higher sensitivity, where on the right side it's much lower sensitivity. And sort of conversely, with the negative ions, our halogens, our carbon, oxygen, and some of our heavier metals are higher sensitivity in the negative mode. And so that's kind of a ballpark kind of reference. And you can see that there's certain elements which you'll really struggle to detect, nitrogen and some of the noble gases, because they're just hard to ionize. Okay, so exactly, I'll just go through a little bit as a principle of how it operates. We tilt the sample, so generally, effectively, you can, wherever the FIB scans, you can collect data. However, usually the way it's operated is we tilt the sample so it's normal to the ion beam is normal to the surface, and we raster over a square area. And the longer you raster, the more data you collect. It's conventionally done at sort of around 20 kV accelerating voltage on the FIB, but you can use lower to improve your depth profiling. You get less layer mixing, or you can go higher and you can actually get higher resolution. So you alter those parameters to suit your analysis. And you can also alter the current density of the ion beam to ideally to match the pixel size in the ToF-SIMS map with the probe size, or approximate the probe size in the FIB. And so we select a square area. If we want to do a small square, we use a low current, or a large square, high current. Most of the time we're using kind of analysis areas in this kind of range, which takes advantage of the high resolution. If you want to go, you can go larger, but generally speaking, if you want to go larger, you potentially other analytical techniques such as EDS might be more appropriate. And the amount of material you remove just depends on how long you raster the ion beam across. The software is quite neat in the sense that you can either do a 2D analysis, or you can do a 3D analysis or depth profiling. So that gives us a range of advantages. And the data is kind of collected as a data cube. So for every pixel, there is a spectra. So we can actually subsample that data cube to extract information from a very specific region, which has a number of advantages, which I'll discuss a little bit later. So we choose either to do our analysis collecting positive ions or negative ions. This is a kind of a rule of thumb, so to speak. So generally, you find you do I find I do a lot of my analysis in positive mode. But if I'm going to do negative mode, I'm usually chasing carbon or oxygen or some of the halogens. So you choose your analysis and you run your ion beam. So yeah, we can do basic surface imaging. We can do spectral analysis. So you compare the intensity or the peak area of one isotope compared to another, and that can be used for isotopically doped material. And there is a potential to do some semi-quantitative analysis from the mass spectra, but there's a number of challenges in terms of quantifying SIMS data. It's a bit more challenging than EDS data, and I can discuss that a little bit later if you have a question about that. And then the other application is depth profiling. So looking at the intensity of a particular ion as you sputter material away, and you can calibrate the sputter time with depth by measuring the depth of the pit. So like all techniques, there's always a number of biases, and they just need to be understood and taken into account where possible. So one of them is surface topography. So ideally we like to work with flat samples, but some of the samples that have topography, you'll get higher secondary ion yield at those locations where you have such an edge or a sharp point. Ideally, you get the best results on conductive materials, although we often work with insulating materials. So when you can use the electron beam to charge compensate, it's a matter of matching the supplied electrons by the SEM with the removed electrons by the gallium fib, and it's quite a neat application that you can charge compensate using not a flood gun, but just the electron beam already in the chamber. So vacuum and contamination issues. So I mentioned that if you don't have a very high vacuum, if you've dirtied your chamber using samples that are outgassing, things like that, you may have some contamination issues. And then the last resource here is about peak overlaps. So the mass resolution of this technique is fairly moderate. So mostly because the time of flight is not particularly long, and so there can be isobaric interferences, and some of them are problematic, and some of them are easy to kind of work around. So a lot of isotopes have a lot of math elements have a number of isotopes, and you just choose an isotope that's unlikely to be an overlap with another isotope. Okay, so commonly this technique is compared with EDS because that's other major analytical technique within the microscope, and there's some advantages and some disadvantages, and it's really good to sort of compare them. So if you look here in the schematic here, the interaction volume with the electron beam is much greater than an ion beam. That's just because the electrons can move much more longer path lengths within the material, any material, than an ion, which has a much higher scattering cross-section. So effectively, the gallium ions come in, they stop very near the surface, and the secondary ions come from a region very close to the point where the primary ions came in. So that's where we get our very high spatial resolution. So the advantages are the better spatial resolution, better detection limits for things like alkalis and rare earths, not so much for things like gold. Depth profiling, because we're physically removing material, we can look below the surface, and I think that's a really major advantage of this technique. Light elements, I'll show you some really nice examples, but the ability to analyze things such as lithium is really gaining importance in Australia at the moment and elsewhere. Isotopic information, so the technique doesn't have the sensitivity for very fine isotopic anomalies, but we can detect some materials that have been engineered with much larger isotopic variations compared to natural abundance, and I'll show you an example a little bit later on that. Large dynamic range, again, that's really good, but the disadvantages are important to take into account. So the spatial resolution is signal limited. So if you're looking at something such as sodium, your spatial resolution is going to be great. If you're looking at something such as gold, which is hard to ionize, your spatial resolution is going to be signal limited. It is much more difficult to quantify than techniques such as EDS, so that needs to be taken into account, and mostly that's because of matrix effects. So the local structure of the material will also influence not just so how easy that is to ionize the ions or the atoms. It is a destructive technique, so once you've analysed the material, you're physically removing the material, and it's not coming back anytime soon. So if you have sensitive samples or valuable samples, you have to take that into account. Surface topography, as I mentioned before, is also an issue with EDS in some cases as well, but it's potentially more of an issue in ToF-SIMS and a high vacuum. Okay, so just comparing a brief example comparing EDS and ToF-SIMS, and so this is some fine particles within a coal. So there's some clay particles within a coal sample, and the backscatter imaging, you can see a bunch of these particles with electrons. We can quite easily resolve them. When we do an EDS map, our spatial resolution is limited by this large interaction volume or information volume of X-rays, whereas the ToF-SIMS is much less limited by that, and we can get a nice spatial resolution chemical map of the, in this case, oxygen distribution within this sample. And then another little neat thing to see is, because the SIMS is only sampling the first say 10 nanometers of the surface, things that might have been seen by the electron imaging, which were below the surface, aren't visible in the ToF-SIMS until you sputter more of that material away to reveal it. Okay, so at this point, I'll have a brief break for questions. So if anyone's got any questions, feel free to ask now. And from then, I'll go through some specific examples from the work that we've done.
So if anyone would like to talk, you can actually unmute yourselves and talk as well. Yeah, Charlie, please. Let me unmute you. Oh, yeah. Yeah, now you can talk. Oh, I think you typed it in. No.
I see there's been a couple of questions asked, so I could probably answer them. So there's a question from Stefan saying, how do you measure depth during a depth resolve experiment? So that's a good question. I'll have an image a little bit later, but effectively the way we do that is you assume, and this is a big assumption, a constant sputter rate, and then at the end of the analysis you measure the depth of that pit using the SEM. And so, for instance, if you sputtered 100 frames of material and then you measured the depth of the pit to be 200 nanometers, so then you can equate that to effectively each frame during the analysis. So each time you scan the full area, you're removing approximately 2 nanometers of material. So if your region, if there's a particular feature that's 10 frames deep, you could suggest that that is a 20 nanometer depth that you've removed for. And that's the way we generally do it. However, the limitation of that is if you're got a layered material which has different sputtering rates, that the initial assumption about the constant sputter rate won't hold true. So you do have to either calibrate it or measure in cross section the depth of the different features. There's another question there from Michael. He asked, you mentioned that nitrogen is hard to detect. Is it yet detectable? It is detectable, but generally only seeing it in things with very high nitrogen. So something like a gallium nitride, you would be able to detect it, but it's not easy. Yeah.
I think Charlie can talk now.
Okay.
Charlie, can you talk? Because you are unmute. If you have a mic, I think you can talk now. So meanwhile, there is another question, Will.
Okay, I'll answer Laura's questions about experience with strontium isotopes. So we have looked at strontium, and I do have an example a little bit later. Not in natural systems, but in material science applications around solid oxide fuel cells. And I'll show you an example of that. Effectively, we have been able to map the distribution of strontium quite easily, but we haven't done any like stable isotope analysis or anything like that. The very fine precision kind of and quantitative analysis of strontium isotopes, would probably be better off with another SIMS technique. So dynamic SIMS.
Just a question now. Would better mass resolution help, Will, for isotope identification?
Yeah, potentially. It's more it's important, but you need to make sure that there's a consistency in the analysis. The beam current's very stable. The vacuum's very good, and there's one of the issues. So if you're measuring adjacent isotopes, so for instance you're looking at oxygen 16 and oxygen 17, you have to take into account that the peak at 17 potentially might not be oxygen 17, but actually be the molecule OH, which will throw out, and you get a lot of hydrides being formed, and that sort of causes some challenges in looking at isotopic ratios. Yep. And that's common in many techniques, SIM techniques.
So we have now 2 more questions.
Okay, I'll answer them, and then we'll finish with the presentation, because some of these questions will be answered in the rest of the presentation. But there will be time for more questions at the end. So I'll just answer Charlie's question. So selective ion etching on depth profiling, it's quite an interesting application. So it's not something I've tried, and would be interesting to see if you can etch just a specific ion. Obviously your depth profiling won't be accurate for all elements, because you'll be leaving some material behind as you move further deeper with the particular element you're trying to selectively etch, and that's yeah. So it's something that's interesting, but I haven't tried it personally. Okay, so Pete Austin asks, how long would a typical analysis of 25 by 25 micron square take? There's a bit of variability in that, so it depends on, so if you use a really high current and you want to remove a lot of material, it could only take 5 to 10 minutes. If you use a lower current, small pixel size, and you want to do some more precision analysis, that could take 20 minutes, half an hour. But generally speaking, none of the analyses are much more than half an hour. So they're generally speaking quite quick.
So just to add to that, after Will is finished with his presentation, I have a couple of slides actually to show about the recent developments in the detector, and also the systems that we can put the detectors on. So yeah, we can have a little bit of more discussion about those after that as well. So thanks for the questions. We can now move on and continue, Will.
Okay. Okay, so moving on. So I'll just go through some specific applications. So generally speaking, there's lots of nice, pretty images, and pretty much everything I'm presenting here has been published, and so there is some references that you can chase up if you're interested. If not, you can contact me via email and I can send you them. Okay, so one of the real advantages, so there is some other type of mass analyzers which are becoming available, but the advantage of time of flight is it's a little bit like EDS compared to WDS. In EDS, you're getting everything, but slightly lower resolution, in that case energy resolution, whereas WDS, you get something specific but a higher energy resolution. So time of flight, we get almost the majority of the elements at the same time, and we can collect that data set and we can generate a compositional map from the element of interest. And this example is a lithium bearing mineral, and we're looking at the relationship of the lithium rich phases with other chemistry. We use that to identify them. This is an application example of light element analysis. So in Western Australia, there's a number of lithium mines, and lithium batteries worldwide is becoming a very high interest commodity. And so we're looking at lithium distribution in the batteries, but also in the material that's being mined. And so we can quite easily, so lithium being an alkali, very, very high sensitivity, we should be able to quantify down to just a few ppm. And we can map an area, so particularly this is 20 microns by 20 microns. We could do that map in just maybe 5 minutes or something like that, and then extract the mass spectra from particular regions. And you can see in this example, only about 1 or 2 microns apart, the concentration of lithium varies very significantly. And we know that the interaction or the information volume is very small, so the mass spectra extracted from there wouldn't be convoluted with the mass spectra extracted from an adjacent region, which is not what you can do with EDS, where you're limited by the large information volume. So trace element analysis, so for our high sensitivity elements, and so for instance the rare earths and alkalis, we can extract information from them, whereas other techniques such as EDS wouldn't be able to see it. So in this example, it's a zircon grain, so zirconia silicate oxide. But when we map it, obviously we would get, in our mass spectra, we get zirconia and zirconia oxide. But we also get a number of other peaks which are very interesting. And so we can map the distribution. In this particular example, we found that the distribution of trace elements was strongly linked with the cathodoluminescence signal, which is associated with gross zoning. But this particular grain had some substructure which was related to some shock metamorphization of it, and that causes a trace element segregation to specific structures. So that's quite neat that we were able to map that quite easily within a FIB-SEM. Isotopic information. So this is another neat information where we combine our very high resolution electron microscopy. So we can, looking at these zinc oxide nanowires, so they're only approximately 200 nanometers wide. And we can do EDS on them, and it tells us that they've got zinc and oxygen, which is useful if that's all you need to know. But if you want to look at the isotopic enrichment, so zinc has a number of isotopes at 64, 66, 67, and 68. And we can look at that. And so this is the natural abundance one. You can see the range of isotopes. Where it's been enriched, in this case 66 enriched, 64 enriched, and 68 enriched. We can quite easily determine that on just a few nanowires, which is really good. So you're combining your high spatial. So you're doing isotopic analysis on very small materials, which is really, really cool. And we can measure the peak areas of these particular mass spectra, and we can actually do some relative abundance analysis, and we have done that. Okay, depth profiling. It's a really neat application in materials science. So we've looked at layered structures. So in this case, vertical cavity laser. I forget the SE acronym, but and one of the ways that they focus the laser output is by oxidizing from the outside in. Now they oxidize a specific layer a few microns below the surface, and so we wanted to look at the extent of oxidization, and so we did so this is just a FIB-SEM cross section to look at the layers. But when we did ToF-SIMS from the top down, so normal to the surface, straight down, we can see the concentration varying through the layers of the gallium and the aluminium. And what's quite neat is we can analyze gallium with a gallium ion source, a primary ion source. And gallium has two isotopes, one at 69 and one at 71. Our FIB has a monoisotopic gallium 69 source. So any gallium 71 analyzed by the ToF-SIMS is sample related, not primary ion related. And so when we look at the cross section of our analysis, so this is our depth profile. This is a effectively that imaged in signal intensity, and you look at the various ions beside itself. We did some negative analysis and we did some positive analysis. You can see oxygen in positive mode, there's very little signal. In negative mode, you get much higher signal. And this particular layer, about 600 frames down, is the one was of interest to us. And so this is looking kind of in the Z direction. And then when we extract that data in 3D, so you got X, so Y, X, and Z here, we can then generate a 3D image. And I'll just show you the video. Just have to try get my pointer working again. It's on the laser pointer. Okay. So you can see here, we extracted all that data and we combined the oxygen, the aluminium, and the gallium data sets, and then you can see you can process this data in normal 3D analysis software. In this case, it was done in Dristy, and you can see the oxide layer at the surface, which is a silicon oxide. There's a layered structure through, and then at certain depths we get the edge of this oxidization layer. And so this video is just sort of showing, turning on the various layers, and it can show at a certain depth we get this intrusion of oxygen, and we were interested in how far it intruded, what was the shape of the edge. So it's quite a nice 3D analysis. You can obviously do that with FIB-SEM slice and view, but the advantages here is we don't have to produce a trench around it. We can just slice straight from the top down, and so it's quite fast. The disadvantage is, as people will probably mention before, is the potential issue with varying sputtering depths, sputtering rates with depth, and so that's why we use the SEM to look at the layer thickness, and that's quite useful. Okay, so then my last examples here is related to solid oxide fuel cell research, because it's one of the things we've published quite a number of papers on, and ToF-SIMS has been really useful for them. So they're looking at these solid oxide fuel cells, and they've got a cathode and a porous electrode, a porous electrolyte, solid electrolyte, and they kind of analyze the interface between these particular layers, and the particles that are actually in contact are very small, and ToF-SIMS has a spatial resolution to analyze these tiny little particles. I'll just put my laser pointer back on, and we can then combine that with a sort of a workflow which involves doing the electrochemical testing. So on the doing our conventional SEM analysis, identifying the region of interest. So in this case here, we're looking at the interface between and this is lanthanum, strontium, cobalt, iron-based electrolyte with the yttria-stabilized zirconia, and we look at this immediate interface, and we can depth profile the concentration of strontium at the interface. We can do lateral imaging of the strontium concentration. You can see here there's a grain boundary in the yttria-stabilized zirconia with a slight depletion. And then when we've sort of done our ToF-SIMS either in the same area or slightly adjacent area, we can do site-specific sample preparation in using the TESCAN LYRA Ga FIB-SEM and do a TM and TM EDS. And in this case here, you can see the strontium layer in the top 30 nanometers links very, very clearly with this strontium layer outside of the particles that are sitting on top of it in the TM EDS. So our depth profiling matches these results. And this is another example of that, where we did our depth profiling. So our FIB-SEM was used to measure the depth of our pit, and that converted the depth to frames, so the frames to depth. And you can see once again the same profile. But if we, in our data set, just look at the first 10 nanometers of data, you can see that strontium is fairly distributed across the surface. And if you look in the EDS as well, you can see kind of strontium everywhere, but in between the large particles, there's only this sort of 20 or 30 nanometer layer. And so once that layer is sputtered away, the strontium then is isolated in these coarser particles. And so it's quite neat that we can extract different kind of distribution maps within the depth profile. Okay, so in summary, it's in my opinion, quite a neat technique for sort of really nice compositional analysis. And the big point is in situ within a FIB-SEM. So it's not the best ToF-SIMS in the world, so it's not the highest mass resolution, but it's a combination of the FIB-SEM with a ToF-SIM, which really gives a range of really neat applications. And so you can do your ToF-SIMS at the same time as doing your preparation for other analyses. So we're applying this to a range of different projects. Some of our publications, or it's probably a few more to be updated, but we put them up on our ResearchGate. If you're interested in them, you can see them there. So with that, thank you for your attention. And if you had any questions, let me know.
We have a question in the question answer box from Stefan.
Okay. I just can't see it.
It says, are there any coating that help with data acquisition or signal improvement?
Are there any coatings that help with data acquisition? Yeah, the issue with the issue with coatings is if you because you're physically removing material, if any coating that you put there, you're actually going to sputter that away earlier in your analysis anyway. So generally not. There is some really nice work being done at ETH in Switzerland on signal improvement, so particularly for negative ions. So there's a low sensitivity, generally speaking, for negative ions, and by that they actually use a cesium kind of vapor that they spread across the surface, and that improves the secondary ion yield for some negative ions. And so if you go to Google Scholar, you should be able to find some publications related to that.
So as you see, Will's email address is there. So if you have any questions, you can easily contact him. I've got the permission already. And I'm sure he's got actually even more data to share if you guys privately contact him, because this was a public webinar and we couldn't really share everything that they were working on. Totally understandable. There are just a few slides that I'm going to show. So, okay. So as Will mentioned, and thank you so much for the presentation. I hope everyone enjoyed it as much as I did. Is my screen shared now?
Yeah, I can see your screen. Okay.
So just a few points about the hardware. As Will mentioned, the ToF-SIMS detector comes from a Swiss company called ToFWork. TESCAN started actually working with them around 8 years ago, and it took them a good 2 years to do the integration well and get a good software running on the system to make this a reliable and useful system. So since it's changed a bit, so William had his ToF-SIMS detector on a gallium fib, as he mentioned a few times during the presentation. At the moment, you can have that on plasma fibs too. And very soon we will have one of these ToF-SIMS detectors actually on a plasma fib at ANSTO. So later, maybe early next year, you guys can maybe get in touch with ANSTO Microscopy, Joel Davis and his colleagues, to maybe see that system and how maybe if you could get access to it. So if we use plasma fib instead of gallium, there are a few benefits or pros and some cons. So I'm just going through those. So xenon plasma generates lower resolution image because the beam is much larger. However, xenon ions are a lot more heavy, which means the ionization rate could be a little bit improved. So in general, if we compare the two, as you see, we will lose a spatial resolution if we go from gallium to xenon by almost 100%. Means if we get better than 50 nanometer lateral resolution with gallium, we kind of get around 100 nanometer with xenon. But because the current density is much more, you can actually ionize more and get more material removed, and you can generate larger data sets in shorter times. Also, as again we'll mention, gallium could be a problem in some analysis because your material can have gallium and you are interested in that only. And again, xenon can be a great alternative because it's an inert gas, doesn't have any interaction with your material chemically at least, and it doesn't have gallium, so you can easily detect the gallium only from your sample, not from the beam that you are illuminating the sample with. And again, another point is that because xenons are much larger, the depth of penetration will be more limited, so you might actually get a better depth resolution. It could be around like 3 to 5 nanometer in some cases. Another benefit would be a little bit improvement in the detection limit, which comes from a better ionization rate with xenon. So if we just consider 5 ppm as a kind of measure that, and again, as William mentioned, that's very element dependent, it will be kind of 100% better with xenon, so you get 2 ppm. And another benefit of using plasma fib is that you can replace xenon with any other gas, like oxygen, that we have plenty of data about. And oxygens actually are better even than xenon and gallium both for ionization. So you might improve your detection sensitivity going from xenon to oxygen. So that's a summary of specifications that you can expect from a gallium or a xenon fib. But there was another development very recently. So this is the CTOF that William has on his machine. C stands for compact. So recently, the optics of that detector are retractable as well, which means you can actually retract your detector or get it closer if your fib is not very busy, which means better collection. And also, a new version of the detector was out maybe a year ago, which is called ToF. So it's got a bigger chamber for mass identification, which means better mass resolution. So with the ToF, which is standing for high resolution ToF, the mass resolution goes from 500 to almost 4,000, which is a great improvement. And it allows actually for more accurate isotope identifications and gets rid of a lot of overlaps that we might have with the C version of the ToF-SIMS detector. And this is just the data set showing when mass resolution is helpful. So with the CTOF, we almost cannot say if we have this is isotope of iron or silicon, but with the ToF, we can clearly distinguish them. So I conclude this now with going back to questions, because I think we have a few more questions now going on. So I'll stop the sharing. So William, Charlie is asking if you can do any bio applications. Have you tried at all?
Yeah, I'll just type in an answer. I'll just send it, but I'll mention it as well. It's potential to do it, and it's actually an interesting application. We can obviously do elemental analysis on labeled samples, similar to what they do in NanoSIMS, but NanoSIMS has a higher precision in the analysis of the specific labels. Although we can do the gallium and even the xenon, the high energy density tends to break most of the molecular bonds at the surface. So you will analyze it. So for instance, if you're analyzing an organic phase, instead of sort of getting a molecule from that organic, you might just get carbon and oxygen. So because of the energy density of the primary ion source was too high. So the molecular analysis with ToF-SIMS is usually done with an argon cluster source. So instead of a single gallium or xenon ion, you actually use 2,500 argon ions or something like that. And that energy may be the same amount of energy, but spread out over a larger area, which means you damage or you break less of the bonds of those molecules. So yes, it can be done. Potentially a plasma fib with a oxygen or a argon cluster source, maybe a tricolumn fib with different sources, will open up a lot more applications. And so I see that is possible. It's not easy with just a conventional gallium or xenon, but it's something that we're looking at too.
So I can add a couple of points to that as well. So TESCAN very recently did some experiments for biomaterial with using a cryo stage during ToF collection, and that improved the consistency of the molecular kind of structures, or at least allowed them to use some of the material that they cannot really normally put into the FIB and analyze them. And the results were quite promising. But as Will said, it's a new field. There are a few parties right now collaborating actually to get some applications on biomaterial done. And I'm sure soon we will have some results to share with you guys. And again, in addition to what Will said, when you have a plasma fib, you can easily change the gas from xenon to other gases that can generate plasma. So oxygen would definitely help a lot because it's less invasive than gallium and xenon. And also, yeah, again, as mentioned, argon would be the best maybe choice for that sort of application. And you can easily shift from xenon to argon. So I hope that answered the question. With this, I conclude today's webinar. And again, thank you all for attending and wish you a very good afternoon. Goodbye.